Hello, welcome. Welcome back. All right, let's get going. How's everybody doing? Great. How are people doing in the back? Also good? Anyone having a bad day? Nobody's having a bad day. I suspect, oh, okay. Well, I'm sorry about that. I hope it gets better. What is a better solution to your problems than a class of 537? It's a question I often ask. Of course, apparently from your reaction, you're thinking that's not the solution to people's problems. Okay, my apologies for that. Okay, maybe it will be. Uh, all right, is everybody ready to go? Okay, things are starting to get serious. October is upon us, which means the semester is no longer just that beginning where we have fun and it's all new and boy, this class is going to be so fun and all the reality of school sets in. So let's brace for October and remember that there's still November and part of December, deep into December ahead of us. What are we talking about? We're talking about the last virtual memory technique that we're going to be talking about really is paging, and everything we're going to talk about is how to make paging work well, because that's basically a very good technique that's used on modern systems today. Paging, as you recall, let's think of it like this. We have, let's use some colors here. Let's say we have a few processes, process one, and another process over here, process two. Now, each of these processes have an address space which is chopped into some number of pages. For simplicity, I will just have 4 pages in each of these address spaces. So that sounds like that'll be easy to keep track of. And if you remember, we have, in reality, of course, what we have is we have a physical memory sitting here with some number of pages inside of it. So that gets to the basic idea that we're something like this, that we're dividing physical memory into these slots, which we sometimes call a page frame, but I will easily just call them pages too. And we're dividing virtual address space. This is a virtual address space over here. We're dividing that into fixed size pages. And of course, these are the same size. And simply what we're doing with paging is allowing basically somehow the system is supporting this notion that each page can be relocated or placed in any one of these page frames as a very flexible way to virtualize memory. So for example, this page here may be mapped to here, and this, let's do a slightly different kind of pattern. This page here might be mapped to here. Similarly, we might have this page here to some location here, and maybe, I don't know, this more solid page here might be right here. Doesn't really matter. I can pick any physical frame for those virtual pages and everything's fine. Doesn't matter. It's completely independent of location. So that's how we're going to virtualize memory. Now the key construct we have is we had the notion of a page table. And that's just the data structure. It's per process. There is a type of page table called an inverted page table. That's actually just one for the whole system. But generally, the page tables we'll talk about are per process structures. And as we learned last time, they can become really big. They can become really big because if you have a large address space, you have a lot of pages, and you need an entry for every page telling you where in physical memory perhaps that page lives. So they can become pretty large, and because they can become large, that implies that they're in memory somewhere too. So for example, we might have, I don't know, in some page here, it's going to be hard to draw this. I'm just going to draw something like this and say, in here, there's the page table for process one. And this is clearly going to be memory that the OS owns. So the OS sits in memory too and has data and code and all sorts of things. And so somewhere in OS memory is the page table for process one. Similarly, somewhere in OS memory, and that could be another page entirely, is the page table for process two. And again, this is owned by the OS. The OS owns that page and puts that page table there. And of course, if it's a big table, it's going to take a number of pages, but here I'm just drawing a small page table. Does that make sense? Any questions about that? Okay. So then what's happening on each memory reference? And I need to slightly scroll this, sorry. I'll try to kind of keep most of it here, even though I've lost the labels. But what has to happen upon any sort of memory reference? And remember, that's instruction fetch. That's also any sort of load or store or other explicit memory access, right? Anything that accesses memory, including instruction fetch from the PC, is being presented as a virtual address. The program counter is a virtual address. It's telling you in your virtual address space which instruction you're about to execute. When you have a pointer in your C program, that's a virtual address. When you're talking about calling a function, you're specifying a function address, that's a virtual address. Anything you see in your program is a virtual address, has to be translated to its physical location before we can go to physical memory and actually get the data. So upon every memory reference, and I'll put every there for emphasis, what we need to do is address translation. And of course, what that means is that we're going to have to use these page tables somehow to do that. So let's think about how we're going to do that. We have a virtual address. And we think of that, like we talked about last time, as really having two pieces. One part we'll say is called the offset. This tells us which byte in the page that we're talking about. The other part we call the virtual page number, or VPN. And that tells us which virtual page we're talking about. So in our example up here, we have just these tiny virtual address spaces, and each of them only has 4 different virtual page numbers that could be generated. And of course, we haven't said how big these pages are, but depending on how many, they could be any number of bytes, like a hardware determined kind of thing, very likely. So they could be like a 4 kilobyte would be a normal page size. And then the offset would be, as many bits as needed to describe, to be able to address all the bytes within that page. So when we're talking about translation, the important thing to remember is what we're translating is we're taking the virtual page number and turning it into a physical frame number, right? So this page was going to here, this one is going to here, this one is going to here, and this one is going to here. And so what that means is in hardware, somehow, the VPN has to go into whatever is doing the translation. And you can think of that as being our memory management unit. And it does the translation, and it shoots out a physical frame number, right? I'll write that out since all these terms, there's so many terms around these things that we have to kind of suffer with a bit in order to be fluent in our discussion of operating systems. So anytime you're learning anything new, you're trying to understand terminology because that's just how everybody who works in that space talks about things. And so you're a little bit stuck memorizing terminology and getting used to it and understanding it. It's not always sensible, it's not always coherent and logical, but there's just ways people talk about things. So you're a little bit stuck with that. Here we're talking about taking a VPN, virtual page number, and turning it into a physical frame number, and that's this process of translation. And what you can see is that the offset is not translated. And hopefully that makes sense to you, why that is. Sorry, that's supposed to be the same size. It's not translated. Well, why, if you were describing that to someone, why would you say it's not translated? Why does that make sense that it's not translated? Yeah. Yeah, it's the same byte in that page, right? We're just saying here, we took some page and we put it over here. You know, we thought it was our virtual page 1. It was actually physical frame 100. But the byte within that page, it's at the exact same offset within that page. There's nothing that's changing about it. Doesn't matter which, because these are all aligned. So the offset doesn't get translated, but the page number does, from VPN to a PFM. And then once we have that translation, we can, of course, go to the physical memory. Then we have a fully formed physical address. It's just concatenating those two things, offset with the physical frame number on the top. Any questions about that? It's a basic process. Okay. What it also means is, remember, this is happening all the time. It's happening on every instruction fetch. It's happening on loads and stores. And it means the hardware has to know stuff about the page table in order to be able to do this translation. The most fundamental thing the hardware needs to know, hardware, H/W, sometimes hardware, one of the most fundamental things is the location of the page table. And so inside the MMU, there's going to be a register. And that register is often called the page table base register. I'm going to write that out so you can see what that is. I'll write it down here. And all that's going to hold is the address of the beginning of the page table of the currently running process on the CPU, right? So if we're looking at our picture here, when the blue process 1 is running, the PTBR is going to point to this page table right here. When the orange process, P2, is running, the page table base register is going to point to its page table right there. And you can already see then there's an OS role in kind of giving the hardware some information. Remember when we were switching in the base and bounds approach, we were switching between process 1 and process 2. We would switch the base and bounds registers because each process's address space was at a different location. There we were telling the hardware, here's the beginning of that address space in physical memory, and now we're switching into process 2, here's the beginning of that address space. That's what that base register was. This is kind of similar, but instead of telling us where the address space is, well, we actually can't do that anymore, right? Because the address space is spread out in a bunch of pages in physical memory. Instead, what this is telling us is where the page table is, which has the information about where all those pages are. That's what the page table base register is doing, and it allows the hardware to do these translations correctly, I guess. That's the page table base register. Any question about that? Does that make sense? The page table base register, I guess I'll write that down, is it points to the start of the page table of the currently running process. Make sense? Is that clear? Can any process update the page table base register? Answer, doesn't seem like it. Why not? Yeah. No, why not? Yeah, you could cause all sorts of problems. You could point it to some page table that says you have access to every page in the system, and then you could start reading and writing anything in the memory. So clearly updating the page table base register is a privileged instruction, just like updating the base register in our old approaches, right? So it's a privileged register. You can think of this as privileged. and only the OS is going to be allowed to update it. And we'll see this when we look at XV6 and we look at x86 architecture. We'll see a page table base register, and you'll see how the kernel can indeed update it, but you certainly can't from user level. So if you think about all the information needed to do these translations, actually almost all of it is living in memory. And all we're telling it is in the translation hardware that's on the CPU is like, where to look. And then it's going to go look there and do the translation. So let's, so any other questions about that or any other thoughts about that? I don't usually ask for thoughts, so I don't know why I did that. It just came out. Sometimes you're up here saying stuff and it just happens. Yeah. Yeah, great. So when I for example, that's a great question. How does that value get there in the PTBR of the page table? That's kind of what you're asking. So what's going to happen? A new process gets created. When a new process gets created, the OS has some responsibility. What's one of the things that OS is going to do? It's going to allocate memory somewhere in physical memory, somewhere in here, in this physical memory, that is for the page table for this newly created process, right? So it's going to create that space, it's going to allocate it, and then somewhere for that process, like in the process list, it has information about every process. One piece of information you're going to store for every process is where is its page table. That way, finally, when you go to run that process, you're going to do something very simple. You're going to take that memory out of the process list. You read it from the process list, and you'll update the PTBR with it, and then you'll jump into that process by returning from a trap and start running. And then when it starts running, it starts to use that page table. When a timer interrupt goes off or whatever else happens, we pause that process. We want to switch to someone else. We're going to do the exact same thing. We're going to read what their PTBR value should be, and then load it, and then start running that process. So it's fully kind of this protocol between the OS and the hardware that we manage the contents of the page table base register. Yeah. Yeah, great. So the question is, when the kernel code is running, what's going on with that? That depends on a lot of things. For now, we've been in a very simple mode. We're kind of imagining that when the kernel runs and when kernel code is running and it's accessing kernel data, that's all in just physical memory. So that would mean that when we jump into, say, privilege mode, no longer are translations happening. So the hardware would know not to do that. As we'll see when we talk about actually a modern system, OS has actually used some virtualization for themselves too, because it's very convenient. And so at that point, that means they have a page table they're operating out of as well. And kind of weirdly, how people did that for many years is you actually have, this is getting a little ahead of ourselves, but I'll preview it and we'll talk about it a little bit later. What the OS often did was it would map its own code and data structures into every virtual address space that exists. So when you trapped in the kernel, you're still in the same virtual address space, and you'd use that virtual address space for the OS code and so forth. It just wouldn't be accessible by the user code because it was protected in different ways. Nowadays, because there's some security holes, which maybe we'll talk about, they're very sophisticated. There are a couple of very interesting hardware bugs that people may have heard about if you pay attention to security, called Meltdown and Spectre. Has anybody heard about those? A few of you. So for years, we've been building hardware with certain assumptions about, how we build secure systems. It turned out some of those were wrong. And so people have actually changed how the kernel's mapped into virtual memory by giving it its own, it's called this kernel page table extension in Linux. There's a lot of detail there that we probably won't quite get into, but maybe we'll talk about at some point in the course. But long story short, for now, we're just assuming everything the kernel does is in physical space, so that's not getting translated at all. Other questions or thoughts? Yeah, just like with many things, though, you'll notice that, we're just scratching the surface because we're just trying to learn the basics. And in each of those things, people have looked at problems for 10 or 20 years, and there's a lot more detail there. Of course, we could get off into if we're excited about it. But for now, we'll just kind of skip that stuff and maybe come back to some of it at the end of class. Okay, So now we're going to get to the fundamental problem that we're going to talk about today. And the problem is that paging is too slow. And we're going to talk about how to solve that. And it's too slow for a very simple reason. You should always remember this about paging. It's too slow because to do this translation, right, we're doing this translation. Let me write it down here, sorry. Translation requires us to fetch the page table entry. Remember, the page table is full of page table entries. We sometimes call these PTEs. So already we have VPNs, PFNs, PTEs, all stuff you have to remember. Sorry about that. But we have to, in order to do the translation, we have to do an extra memory reference. So for every instruction fetch, first we fetch the translation. For every load or store, first we fetch the translation. Then we're allowed to go to memory and do what we need to. And because of that, we're going to make the system twice as slow, or whatever fraction slower. Memory is very expensive to go to. And if we have to go to memory all the time, it's going to be slow. So that's our major issue for today. And the solution that we're going to talk about is a hardware solution. And it's yet another three-letter acronym, which is called the TLB. It's a historical name. It doesn't really make sense. It's called the Translation Look Aside. Kind of makes sense, actually, but it's an old name. The Translation Look Aside Buffer. I think a better name would have been simply an address translation cache. And all the TLB is a very simple idea. You can think of it as in CPU hardware that holds, I don't know, some number, that's not the right letters, some number of, let's call them popular translations. So if we think about this diagrammatically, let's keep that here. We can think of our old friend, the CPU. Over here we have our physical memory. Of course, when the CPU talks to memory, it has to talk to it in terms of physical addresses, and then it gets back, information, some kind of data. And so that means that the CPU has to present physical addresses, so that those what have to come out of here. And you can think somewhere in the CPU, this is not to scale. You can think of it as being part of our MMU. We're going to have this TLB. And it means literally that every time we have a virtual address, it's going to go into the TLB and hopefully get translated and so forth. And the idea, of course, is memory has all the translations. Remember, like with a 32-bit address space, you might have, with a 4K page, you have something like, well, you have exactly 2 to the 20th possible translations, 1 million translations possibly. So there's a lot of translations perhaps sitting in memory. We're going to keep something like tens or hundreds of the most popular ones right there in the processor themselves, so we don't have to go all the way out to memory and get them. So we're just going to use the hardware right there and do the translation very, very quickly. It's really a simple idea. Again, it's kind of hardware comes to the rescue for us. So let's think about what that means. So the method here or something like that, it means that we have a virtual address like we show above. It's given to the TLB. And basically there's 2 things that can happen. One, if the VPN is in the TLB, we call that a hit or a TLB hit. Then we can simply use the page frame number that's found in the TLB, form the full physical address, and perform the memory access. Very simple idea. So, or, of course, what can happen is, and that's what we're hoping is the common case, right? We're hoping the common case is the thing we're looking for is already in there. Now, what are we assuming? Like if, you're trying to just keep a few translations in this, let's call it hundreds of translations out of potentially millions. We're hoping that somehow these hundreds, we're going to get a lot of TLB hits. What is it about a program that's going to need to be true for us to have a lot of TLB hits? Yeah. Yeah, some kind of locality, right? There's different types of locality that programs exhibit. And what locality really is referring to is a certain predictability of programs. So programs, if you think about a program, just the sequentially executing program, there's a very natural predictability to it. For example, you run this line of code, then this line, and the program counter advances in a very regular way. In fact, on a page, like on a 4K page, you may have, I don't know, 1,000 instructions, something like that. So as you're executing these instructions, remember on a page, there's a lot of information. So if you start accessing the code on a particular page, you're going to use that, you're going to translate that page over and over again. So keeping the translation for that virtual page to wherever it's located in physical memory in the CPU and the TLB is going to be very effective. If you think about, now of course, even better, like what other things happen in code? You have a loop, right? You have like a branch back to some code. So it means you're kind of executing over the same code over and over again. And again, if you think about a page, right? On a single page, this is one virtual page. There are a lot of instructions. And so if you're running down these instructions and then you pop back up, all of them are generating the same VPN, right? The same virtual page number, which means, again, we're just going to be using that same translation over and over again. So even having just a few of the popular translations that have happened recently around would probably do pretty well. Early machines had, 1632, modern machines have more in the hundreds, but it's really not that many. So there's a certain kind of, this is kind of an example of what you might call like code locality. Locality says, basically, if I'm referring to something on this page, I'll probably refer to something nearby to it in the near future. And that's a spatial locality. There's also people talk about temporal locality. If I refer to something now, I'm very likely to refer to it again in the near future. That's kind of in time. And so code is like that. What about data structures? What about data, not code? Does data always have good locality properties? What do you think? Is it likely to, yeah. Yeah, some data structures might naturally, like you have an array, you might scan through it. That might have some kind of locality because you're accessing nearby things all the time. What about like a linked list? Does that have good locality? Well, not necessarily, right? Because eventually what a linked list is, if you think of a linked list, like let's see, we're talking about data locality. Example here, linked list. Well, linked lists have a bunch of nodes, right? And those are just all over the place in memory, as indicated by this terrible diagram. And, you could imagine here's our memory, and the linked list nodes, who knows where they are? You just called malloc and got something back, and they could be all over the place. So to some extent, a linked list can kind of be like a fairly random access kind of data structure, which won't have great locality. That doesn't, there's pieces of it that still are going to have locality. For example, the node itself may have a lot of data elements in it that you're looking at when you look up something in the linked list. So you might hop around a bunch to get to the right node, But then you might use a bunch of the data inside of one of those nodes. And the bigger the node, then the more locality again you kind of have. So it kind of depends, is there a locality or not? Kind of depends how you use a structure like a linked list. An array, again, might have really good locality, well, depending how you look at it. Hash table, maybe not so much, right? Depending how you look it up. So maybe less so. It kind of depends on the program. But an assumption, I guess we should say, behind, oh, sorry about that. An assumption behind virtually any hardware that's built today is that there is some locality, and that locality allows us to build hardware that makes things run quickly most of the time. So there's an assumption that locality exists in a lot of these structures. So, at least somewhat. Okay, so we've talked about the fast path. So if the VPN is in the TLB, great, that's a hit. Then we just use that means that page frame number is in the TLB, it's in a structure really close to the CPU, we can form the physical address, we can go to memory, and we're kind of done. Of course, if it's not, then we call that a TLB miss. And then the hardware has to do some work. It's going to use the page table base register then to access the right entry in the page table. It's then going to update the TLB with the necessary info, the translation in this case. And then basically, try again, which is going to lead to a TLB hit, and everything's going to be fine then. So it's a pretty simple process. Of course, what that means is, our whole goal here was to avoid this extra memory reference to the TLB. If we have a lot of TLB misses, you can't really avoid them, right? That means you're having that extra memory reference to go to the page table and get the translation. 1 second on the question. And so that's really a property of the program, how often we're going to have to do that. But what we're hoping is that there's enough locality that when we go and we fill the TLB with the right contents, that we're going to get a lot of TLB hits, and therefore we're going to normally run at the speed that we expect, which is when we go to memory, we only go to memory once. Yeah, there was a question. Yeah, it's just kind of the exact mechanism of how that happens, it's kind of depends on the specifics of hardware. I think it's just an easy way to think about it. It's just like, now I've updated the TLB. Okay, let me just access the TLB and see how it works. You can imagine there's other ways to implement that. So I think it's easier to think about it that way. So it's more of a conceptual how it does it. Yeah. Yeah. Yeah, great. So good question. The question is, what happens if the TLB is full? Well, what happens, and we'll talk about this with physical memory as well, with any sort of cache, when it's full, you have to do something called replacement. Replacement means, very simply, you kick out something to put the new thing in, very formally. That's what replacement is. So if you have like a TLB here, and it has, 4 translations in it. This is a small TLB. It has 4 VPN to PFN entries inside of it. And of course, what that means is if it's full, if these are all in use, then, we're going to have to take one of them and decide that's one that we're going to remove. Now, let's say that we're using different colors for these different translations. How do you pick? Well, I don't know. What do you think? How should we decide which one to remove? Sorry. Sorry? Oh, sorry, you. Sorry, it's really it's hard to tell like where the voices are coming from because I can't see people's mouths moving. My apologies. Well, yeah, so you might base it on some sort of heuristic, right? Like this one was used the longest time ago, so it's probably not that popular. Now, is that always going to be right? No, it's not always going to be right. You might say pick a random one. We've talked about that as a policy before. You might say pick one that's been least frequently used, right? That's a popular policy. This all is going to be done in hardware. People have used all sorts of different approaches. Is there any one great approach? No. There was another question over here. Yeah, great, great. It depends. The question is, are there instruction TLB versus a data TLB? Are those different structures? Are they the same? Different hardware have done different things. Certainly, you can have often and often do have separate TLBs because those are very different kind of sequences of or streams of accesses. But you don't have to, right? It just depends. Different hardware have been built in different ways. Yeah. Well, I mean, it's hard to say there's much predictability to that. You're right that if you kind of knew something about the structure, you could kind of predict what the next so many accesses are. But you have to have a very deep knowledge of the structure then. You have to be looking in the node and know that it has an entry in the node that's an address that's the next thing. But you're right that, like, for example, let's say you have a linked list, and let's say you're not doing that deep of searches in it. You're going to be accessing the same pages over and over again, and that's going to have a certain kind of locality to it, like you're pointing out. Well, that's a deep question about how much there. If you look at the area of computer architecture, which I don't actively study, though I used to a long time ago, um, you're basically kind of asking me in the thousands of papers that people have written about techniques to do better a job of predicting what you put in a TLB. Has somebody thought about looking into a linked list node to predict that? I'm just going to say the answer is yes. Someone has thought of that. But I can't point you to the paper. I think there was even some work here. So Wisconsin has a great history of computer architecture. And I do think there was some work here that even looked at that sort of like deeper level of analysis, but it's hard to build those things really super accurately. Yeah. Yeah. Sorry. Can everyone be, sorry, a little quieter? I can't quite hear people asking questions. Thank you. Yeah. Yeah, great. So the question is about when you call malloc 1,000 times to allocate 1,000 different nodes, is it going to try to put those near each other or not? And yeah, I mean, I think it would be natural for it to try, but the thing is, over time, like your heap is going to get fragmented. So what happens, deep into the program, despite my intentions, it might be that how you're managing that list doesn't allow for you to do that. But it would be pretty natural for it to do that. And there's some pretty advanced allocators that people have built, slab allocators, things like that. Um, and those tend to, for like certain size requests, try to keep things near each other for these same reasons that we're talking about to kind of encourage locality. But it's hard to guarantee it because we don't know what the stream of requests are going to be. And in a C program, once you give out an address, you can't like move it around. You're stuck with it where it is. And so you'll be a little bit stuck with whatever happened at that time. But yeah, sure, people do try to do things like that. Any other questions? Yeah. Oh, sorry. Yeah, you and then you. Great, great. So you're getting to some issues with problems that we're going to have with a TLB. Like, does it have translations for all processes, just the current process? So we'll get to that. Let's leave that as an open question. Good question. There was a question over here. Yeah. Oh, great. Yeah, I got you. So I think the question is about TLBs and does it have multiple levels in the hardware? It certainly can. Just like caches in hardware today, they have one, level two, level three caches. You can have TLBs that have multiple levels for the same reasons. If you think about why do people build hardware that way, it's easy to build fast hardware if it's really small, right? That's how you get, it just physics says if you want to build something fast, it's going to be small. And so the nearer you get to the processor, the smaller the structure is, but you might want a slightly bigger cache behind that, a next level cache. It's going to be further away. It's going to be a little slower, but it could be bigger then and have more translation. So certainly people have explored that. Okay, let's do one more question here. Yeah. Are the TLB entries visible to the OS? Great question. That's also something we're going to address in a second. Um, for now, what we're assuming is what happens is the TLB is managed by the hardware. So in fact, we're talking about what's called a hardware managed TLB. What that means is that the OS's role is very simple. It's to populate the page table correctly and point the page table base register to that page table. Then the hardware handles everything else. It knows how to look up. Think about how this is a little bit of a weird data structure. The OS is filling a page table, and I say, hey, that's just a data structure. But the hardware on a TLB miss has to look up in that page table and find the translation and put it in the TLB. So the OS isn't really paying attention to what's in the TLB. It's just paying attention to what's in the page table. And I keep failing on that. So, um, so that means the answer to your question in this kind of hardware managed TLB is no, the OS isn't paying attention to it and doesn't know anything about what's in the TLB. After the break, which we'll take in a second, we'll talk about a different type of TLB, which is called a software managed TLB. And the software managed TLB, the OS is actually much more directly involved with updating its contents. And that's a more modern approach that people started doing in the 90s. Great questions. Questions are fun because then we talk about what's on your mind instead of what's on my mind. So that's a very basic idea of a TLB. We'll go a little bit deeper after the break. Let's take a 3-minute break and we'll also talk about other administrative things when we come back.